Namaskar dosto. Welcome you all in this new video, and in this video we are going to discuss a very interesting and very important topic. Okay, and this is not even a topic. Okay, this is the practical importance. Okay, what is this wave function? Okay, of a free particle, and nowadays we discuss about the dual nature. Okay, dual nature, and we know that the particle is moving and in the form of wave. Okay, it means that we see the particle moving like this, but there is a wave that is associated with that matter. Okay, that is called matter wave. Okay, so here we are going to discuss about the wave function. This wave function, that is represented by psi. Okay, this is very important because this is the quantity which represent that material wave. Okay, that matter wave of associated with that particle. Okay, it means that wave function that is represented by the psi is the mathematical expression of a particular wave that is associated with a particular particle. Okay, so after the quantum mechanics, when it evolves, okay, after 1925, when we came when the de Broglie wave equation came into existence, and after that Schrodinger wave equation comes out. Okay, psi wave function is the main and very important component which represent and which shows that there is wave associated with the matter. Okay, with the particle, and that wave is represented through a quantity. That quantity is called wave function. Okay, and in this video what we are going to do, we are going to do that wave function of a free particle. Okay, free particle, we will discuss about the two cases. Okay, first case we will discuss about the classical mechanics. Classical mechanics deals with the when a particle is under a particular force. Okay, and it's about macro particles, not micro particles. And if we talk about quantum mechanics, it means about the microscopic particles, about the atomic level particles. Okay, so first of all, let's understand what is this wave function. Okay, let's understand it logically and practically. Okay, let's start our video. So this is the condition. You see that these three balls are moving like this. Okay, and this is the view when you measure the things under the classical mechanics. Okay, classical mechanics. Okay, if we go further inside the particles, okay, then we saw that this is the actual motion of these three things. Means these three particles are moving in the form of wave. Okay, because the particle inside these particles are moving in the form of wave, and that wave is called matter wave. Okay, matter wave. Okay, and to indicate that matter wave, okay, or to show the mathematical expression or mathematically represent that wave, we use a symbol or that is now called psi, and this symbol is called wave function. Okay, wave function, and we are going to derive the expression for this for a free particle under the classical mechanics and quantum mechanics. Okay, so you have seen that what is this psi. Okay, how we can define this? This represent what? It represent the probability of finding a particle in a particular region. Okay, means what? Where the probability of finding the particle is large, it means that the value of this psi will large. Okay, means here. And let there is another region where the value or probability of finding that particle is very small, there its value is small. So it varies like this. Okay, so means it shows the waves like character, and because of this character we come to know that there is a wave associated with that particle. Okay, while it is moving. Okay, look at here. This is the point where we see the maximum value of psi, means wave function. Okay, and this is the point where we see that the the value of this psi or wave function is 0, means it shows the probability of finding a particle in a particular region. Okay, and this represent the mathematical expression or mathematically indicate the wave that is associated with that particle. Okay, while it is moving. Okay, so this is the actual things and what happen in the quantum level. Okay, how the things moves. Okay, like this, this is the particle which is moving under a particular thing, okay, and where is the, this is the peak point, and that height or that peak, that have the maximum value of wave function, and which is the bottom of this wave, that have the minimum value of this wave function, okay. This represent the practically quantum view of a particle moving, okay, inside a particular body, okay. You can see there is a scale, and here is the measurement of the psi, that is the wave function, okay. In the variation of the value of this wave function, we comes to know that the particle inside a body is moving like this, like in the form of wave, okay. So this is very important, okay. So now discuss that classical mechanics, okay. What we are going to derive, we are going to derive the wave function of free particle, okay. So first of all, we have to know that what is the free particle, okay. Let me change the color of pen. Free particle means what? Free particle means where the force is zero, means no force is acting on the particle, that particle is moving freely. Let that particle is moving with the velocity v, okay. Velocity, v is your velocity, and mass is m. A particle is moving freely, okay, and m is the mass of that particle, v is the velocity with which it is moving, okay. So what, no force is acting on, no any external force is acting on that particle, okay. So what force, we know that force is equal to dp over dt by the Newton's second law of motion, okay. So this is equal to 0, okay, because f is 0, so dp over dt is 0. It means that p is constant, okay. You know that when we differentiate any constant with respect to anything, that comes equal to 0. So p is constant means momentum is constant, okay. And if we talk about kinetic energy of this particle, this free particle, okay, that is 1 over 2 mv square, okay. If we divide m, okay, so here will be m square v square, this will become p square over 2m. When your p is constant, mass is always constant, okay. So p is constant, it means that kinetic energy also will be constant. So here see what is the happening here. For a free particle, momentum and kinetic energy, okay, these two are constant, okay. So this is the case in the classical mechanics. Now we talk about the quantum mechanics, okay. Quantum mechanics means it deals with the microscopic level, okay, it deals with the atomic level, okay. So now we discuss about the quantum level and what is the wave function for it, okay. Let's understand this thing. Let the displacement of wave associated with matter, okay, wait a minute, okay, the displacement of wave associated with matter, okay. What is the displacement of the wave associated with the matter? That is represented by the wave function, okay, and xt. Let the particle is moving in x direction, okay. What is particle here, and this is moving here in this direction, okay, like this. We don't know which kind of the motion it have, okay. It have wave motion. So at particular time t, let at time t, okay. So let at time t, what is the frequency of the wave, that is associated with that particle, that is nu, okay. And what is the wavelength, that is lambda, okay. So this is the factors that we already have, this is the parameters that we already know this thing, okay. So what will the wave function of the wave function, what will be the wave function for this thing? That will be a e I, okay, omega t minus k x, okay. So this is the wave function, okay, for a particle when it is moving along the x direction, and frequency is already given and a wavelength is already given. Okay, so what will be xt is equal to ae minus, sorry, ae minus I means iota, okay, omega t minus kx. From here we know that the value of omega is what, 2 pi nu, okay, and what is the value of k? K is 2 pi over lambda. Okay, so put the value here, ae minus I 2 pi nu t minus 2 pi over lambda x. Okay, so from the de Broglie equation, okay, so from the dual nature of matter, we know that what is the lambda? Lambda is equal to h over p, okay, h over p. So here we will put the value of lambda, and omega value is here. Okay, so this nu is what? This is the frequency, and we know that what, how we can find the energy from this. This is E equal to h nu. This is the expression that we already know. So by putting all these value in this expression, okay, so we comes out with another equation, that is this, okay, is equal to a e minus 2 pi I, okay, and e over h t minus x over h p. Okay, so now take the common this h, okay, we will common this, so a e minus 2 pi over h I e t minus px. Okay, so as we did in the Heisenberg uncertainty principle, we will follow that principle same here. Okay, so this will become e minus I over h dash, okay, and e t, wait a minute, okay, e t minus p x. Okay, so this is the final expression for, wait a minute, this is the final expression for wave function of a particle in case of the microscopic study, or in case of the quantum mechanics. Okay, so on the basis of this wave function, we will derive the Schrodinger wave equation, which is the main and very important proof for the dual nature of a particle under quantum mechanics. Okay, so this is the final expression that we have to derive. Okay, so thank you so much. If you like our video, then give us a thumbs up and do subscribe our channel.